Welcome Algebra 2. We're going to go back to section 3. We're going to look at polynomial functions. We'll start to graph them and talk about their characteristics. Learning target for today says I can use the degree of a polynomial function to determine the shape and characteristics of its graph. And also success criteria. You'll be successful. We're going to start writing equations of transformations of these parent functions. So if you have that transformation chart that you wrote down from section 1, that is going to be most handy. All right. Let's define what a polynomial is. If you recall, we talked about functions. You remember functions are in the form f of x equals whatever you're doing, right? So they're just functions with several terms. And if you look here, this first example, I have a term that's x squared. I have a term of 3x. And I have another term of -1. So since it has multiple terms, it's considered a function. The degree, or excuse me, it's considered a polynomial. The degree of our polynomial is just the highest exponent. So if you look at this first one, this is a second degree polynomial because the highest exponent is 2. The next example, it is a 5th degree polynomial because its highest exponent is 5. Pause if you need to get that definition of degree down. I'm not necessarily worried if you get all of this down, but I do want you to have a good understanding of what it means to have a polynomial in standard form. So again, polynomial, we have multiple terms. So if you take a look at this just general form, we have an x to the power of n. So an is just what we call a coefficient. It's the number that's being multiplied to that term. For example, in this first one here, we have the x to the 5th power term. It has a coefficient of 5. Continuing on to this general form here, we see that in standard form, our polynomials, their terms start to descend, especially with their exponent. So we see that we have the highest exponent. This is a degree n polynomial. The next term is n minus 1. The next term would be n minus 2. The next term would be to the power of n minus 3, until you get to the end where you have coefficient a2, whatever that may be, multiplied to x squared, and then a1 multiplied to x, just x to the 1st power, and then lastly you have a lonely constant at the end. So that's just what it means to be in standard form, is that all of your terms are organized in descending order, so you have the highest degree term at the front. So you can easily tell what the degree of your polynomial is. For example, let's look at that first one. This is a degree 5 polynomial, and I see that all of the other terms are organized in descending order, and then all the way to the 1st degree term, and then that constant at the end. The next one, p of x equals x cubed plus 3. Now, while it is missing an x squared and just an x term, we could rewrite this as plus 0x squared plus 0x plus 3. It'd be the same thing as x to the power of 3 plus 3. So it's still in standard form, even though we're kind of missing those middle 2 terms, just because they have a coefficient of 0. So they kind of disappear. That third example here, definitely not in standard form, because we see that the highest degree, the highest exponent, is not the first term. The first term is actually the constant. That should go at the end, and then this x to the 5th power term should be at the front. Then that would look a little bit more like standard form, right? You just have to reorganize those terms. All right. We're going to also talk about characteristics of our graphs and of our functions. So what does it mean to be an even versus an odd function? Look at the graph. If the graph of your function is symmetrical about the y-axis, then you have an even function. So use the y-axis here. There's that dashed line. We see that the left-hand side of the graph looks exactly the same as the right-hand side of the graph. This is an even function. What does it mean to be an odd function? Basically, it's if you have rotational symmetry about the origin 180 degrees. So if you could take the graph of this function there, rotate it 180 degrees on that center point, and if it looks the exact same, then your function is considered an odd function. Just another little picture, a couple more examples of what it means to be even and odd functions. A great example is x squared for even functions. That thing is definitely symmetrical about the y-axis. Another odd function would be considered x to the power of 3, the cubic function, what we'll talk about in just a second. If you rotated that 180 degrees about the origin, about that origin there, it would look the exact same and it would be considered an odd function. Okay, so we are going to go through a whole bunch of special types of polynomials. We're going to go through the name, we're going to see the function, and we're going to determine the degree and whether or not it's even or odd. So as we're going through these, definitely get down what the name of it is, get down what the parent, what the basic function is, and the degree, and if it's even or odd. We're going to review domain, range, and end behavior as well, but hopefully you don't need to get too much of that down unless you want it for review. Feel free to do so. So if we're looking at a linear function, all right, its function looks something like f of x equals x, right? That's just the basics of it. We could do transformations on it, like maybe we have f of x equals 3x, so like a slope of 3, or f of x equals negative 2x minus 3, right? Those are all linear functions, but they're not the parent function. We're just interested in the most basic version of this. Its domain, again, which is all of the x values, is negative infinity to positive infinity. We can think about this guy extending out forever and ever. Eventually would reach all of those x values. For range as well, all of the y values, if this thing extends forever in both directions, eventually it's going to reach negative infinity and positive infinity. Its end behavior here, again, that describes what happens to the function on both ends. There's two ends of the function, right? So this one says as x goes to positive infinity, as we travel this way on our x-axis, I see that the function is going up, so f of x is also going to positive infinity. The next line as x goes to negative infinity, as we travel this way on our x-axis, I see that my function is also going down, so as x goes to negative infinity, f of x also goes to negative infinity. One thing I want you to notice about these end behaviors is that the ends are different. I mean, obviously, but doesn't matter if x is going to positive or negative infinity. The ends of my function, they're going in different directions. On one side, we're going up. On the other side, we're going down. The degree of this thing, well, it doesn't really have an exponent. We could say that it has an exponent of 1. So this would be a first degree polynomial. I'll say degree 1. Is this even or odd? It's definitely not symmetrical about the y-axis, but if we tried to spin it around 180 degrees on that point, it would look the same. So this would be considered an odd function. Let's kick it up a degree. So what about the quadratic? Again, we've talked about these before. You know that the quadratic function f of x equals x squared. You could have different quadratic functions like 3x squared or x squared plus 5. But again, we're just focusing on the parent functions, the most basic version of these. So domain, we could include all positive numbers and negative numbers. We could go from negative infinity to positive infinity. Our range here, all of the y values, is limited to everything above 0. All right, so again, we see that starting off here at 0, the function only goes up. So the range could be written as 0 to positive infinity. End behavior, while the end behavior of our last function was different, on one side we went up, on the other side we were going down, end behavior here is the same on both ends. As x goes to positive infinity, f of x goes to positive infinity. And as x goes to negative infinity, f of x still goes to positive infinity. So the end behavior on the quadratic function is the same. They're both going to positive infinity in this case. The degree of it is just a second degree polynomial. And this thing is definitely going to be even. If I drew that line of symmetry down the center on the y-axis, looks the same on both sides. Okay, we're going to start going a little quicker through these. Cubic function has a function that looks like f of x equals x cubed, x to the third power. Domain includes all real numbers. Range includes all real numbers as well. And the end behavior, again, we see the end behaviors are different on both ends. On one end, we're going up. On the other end, we're going down. The degree of this thing is definitely a 3, and it is considered an odd function. Next one here, we'll kick it up another degree. So let's talk about f of x equals x to the fourth power. This is a quartic function. Quartic function, that name is right there. Domain is all real numbers. Range, again, we see is limited to only positive numbers, similar to our quadratic function. So our range could be thought of as, well, anything from 0 all the way up to positive infinity for those y values. End behavior, again, we see that, hey, it's the same on both ends. Doesn't matter if x is going to positive or negative infinity, f of x is still increasing on both ends to a positive infinity. The degree of this is degree 4, and it's an even function. So we're seeing these kind of, it's either flip-flopping back and forth between even or odd. We see that the end behavior is also flip-flopping back and forth between even or odd. One more, parent function is now called the quintic if we are discussing functions that are f of x equals x to the fifth power. Domain and range, all real numbers from negative infinity to positive infinity. Here we see that the end behavior is different, right? On one side, we're going up. On the other side, we are going down. The degree of this thing is 5, and it is definitely an odd function. Okay, that was the quintic. If you're dealing with any other parent functions like f of x equals x to the 6th power, or f of x equals x to the 10th power, we don't have any fancy names for those. We just say, you know, the 6th degree polynomial. So quintic, quartic, cubic, quadratic, and linear are the basic ones that we're going to discuss. So anything with degrees 1 through 5. Okay, so I want you to take a look at this graph here. On the left-hand side, I have the linear function. I have the cubic function, x to the 3rd power. And I have the quintic function, x to the 5th power. On the right-hand side, I have the quadratic function, x to the 2nd power. The quartic function, which is x, well, that was terribly drawn, I'm sorry, x to the 4th power, and also added in there is a polynomial with degree 6. So over here I have all of the degrees that are odd, and hey, check it out, they're odd functions as well. They have this rotational symmetry of 180 degrees. On the right-hand side, I have all of the even functions. They have exponents with even numbers on them. And check it out, they're also even functions. They're symmetrical about the y-axis. And one thing I was trying to point out to you is that our end behavior was switching, right? If you are, so basically this is what I'm saying down here. If you're a parent function and your degree is odd, like x to the 5th power, your end behavior is going to be different on both ends. So for example, as x goes to positive infinity, f of x is going to go to positive infinity as well. It's increasing that way. On the other hand, as x goes to negative infinity, f of x is also going to go to negative infinity, right? So it's different on both ends of your graph. However, if you are a function that is even, like x squared, or x to the 4th power, the quartic, or x to the 6th power, or x to the 12th power, right? If you have a degree that's even, your end behavior is going to be the same on both ends. In these examples that we covered, we were both going up. So for example, as x goes to positive or a negative infinity, f of x is going to positive infinity for these examples as well, all right? So some interesting characteristics pop out depending on if your degree is odd or even. Let's talk briefly about graphing some of these polynomials. When we graph polynomials, it's really nice if we can pick 3 reference points so we can see the end behavior start to play out here. So for example, let's graph x cubed minus 1. And you may want to sketch a coordinate plane in your notebook. X cubed, it's got a degree 3. I know that it is a transformation of my cubic function. So this is going to be a cubic function. I'm just going to sketch out the parent function of my cubic function. So it looks something like this. That's not the graph of x cubed minus 1. This is the graph of x cubed. If I wanted to graph x cubed minus 1, which I will do in green, I know that this is just a vertical shift. Again, this is kind of calling back from your transformations page from Unit 1. That minus 1 there is going to be a vertical shift. So it's going to take my function and move it down. Everything's going to move down 1 unit. So it should look something like this. Let's graph some points, some reference points, so we actually get that exact graph, a very accurate graph of it. So let's just pick x equals 1. If I plug, x equals negative 1. If I plug x equals negative 1 into my function, you're going to have f of negative 1, which is negative 1 cubed minus 1. Negative 1 cubed is negative 1 times negative 1 times negative 1, which in the end is just negative 1. So this is negative 1 minus 1, which is negative 2. Sorry, that was a lot. I'm going to back that up here. So my f of x value, the output is just negative 2. And that's a function that that's a point that I can graph. So negative 1, negative 2 right there. What about when I plug in x equals 0? Well, then I'm going to have 0 to the 3rd power minus 1, which is just 0 minus 1, which is just a negative 1. Again, that's another point that I can graph, 0, negative 1. And then if we pick x equals 1, well, let's plug that in. So 1 cubed minus 1 is just 1 minus 1, which is just 0. Again, a third point that I can graph. Now I can see my cubic function. I know the shape of it has to look something like this pink line. And I know everything just got shifted down. Looks pretty accurate to what I was sketching earlier. Okay.